こんにちは、阪大産経の田中です。今日は菅先生や田島会長も提言している物理学会の英語化の試みとして、日本人ですが、日本人を相手に英語講演をやってみたいと思います。拙い英語ですが、どうぞよろしくお願いいたします。Okay, so I would like to talk about our recent result of the momentum result resonant photoelectron spectroscopy of titanium-2. The main interesting point here is probably the first observation of the negative Q value in the final resonance in the history of the resonant photoelectron spectroscopy. The titanium-2 is one of the typical TMDC, transition metal dicarbonate, and it is known that it shows the CDW transition, charge density wave transition. In titanium-2, the driving force of the CDW transition is believed that the exonic interaction, this is formed by the charge transfer from the valence band to the conduction band. Usually, it is said that the conduction band at the M point is contributed for the titanium-3D, and valence band at the gamma point is from the Selene-4p orbital. It is very typical characterization. However, this assignment has not examined experimentally as far as I know. So I believe it is worthy to investigate this system using the resonant photoelectron spectroscopy. Okay, the experiments were carried out using the momentum microscope. It is installed at the UV-Sol synchrotron facility of IMS. Since Professor Matsui gave the lecture about it 2 days ago, I skipped the detail. But one thing, the experiment shown here is made using the single type equipment, but it is now under reconstruction into the tandem type with a very new spin analyzer of high efficiency. Okay, the single crystal of titanium-2 examined here is cleaned by the cleaving in the UHB, and the measurement of temperature was all the room temperatures. Okay, let me show you first the X-ray absorption spectrum of titanium-2 at the titanium-2p absorption edge. Then the ABES EDCs taken at these photon energies are shown here. We took 3 points in the brilliance zone, M and equivalent M prime and gamma. Then here we refer to the peaks near the Fermi level as A for both at the M and gamma points, and the peak at the binding energy of 2eV at M as B. Well, obviously the EDCs drastically change when the photon energy varies. So let me proceed to the constant initial state spectra, where the intensity of the specific binding energies in ABES is recorded as a function of the photon energies. Well, they can be categorized into 2 parts. One is the CIS of the peak A. Well, they are very similar to the X spectrum, except one extraordinary thing. There are energy shifted component is strongly observed at the 0.6 eV lower than the XA's peak position. They are attributed to the surface and or the defect side, but the detail is not discussed here anymore. Anyway, the similarities to the X-ray spectrum strongly suggest that these photon peaks are significantly contributed by the titanium-3D orbital, both in conduction band bottom at the M point and the valence band top at the gamma point. This is obviously not consistent with the classical picture that the valence band is made by Selene-4p orbital only. This is confirmed by our DFT calculation shown here. The peak A is definitely made by the hybridization of Selen4P and Titanium-3D. Okay, let's move to the peak B at the M point. But before discussing at the detail of the CIS spectrum, we identify the peak B using other methods. There are two evidences that this peak B is made by Selen4P, predominantly Selen4P orbital. One is a DFT calculation shown here, right, left, and the other is a photon energy dependence shown here, right. In short, the photoelectron cross-section of the Titanium-3D orbital becomes much smaller than that of the Selen4P orbital at the photoelectron range we used. Thus, in our result, the Selen4P peak is enhanced compared to the Titanium-3D peaks, and at lower photon energies we observed, this peak B is not observed. Okay, we will see the resonant behavior of the peak B, Selen4P derived peak. Obviously, it shows the threefold symmetry, and there is a huge difference in the CIS spectrum between M and M prime. Although these are equivalent points with respect to the energy levels because the crystal has a sixfold symmetry. This must be caused by the matrix element effect in the photoelectron emission process due to the photon polarization. Our observation has shown that the Titanium-3D derived peak, such as peak A, shows nearly the sixfold symmetry in the angular distribution. Therefore, we can deduce the true peak B contribution by removing the background after taking a difference between M and M prime. Okay, the result is here. I also put the CIS spectrum of the whole valence band, which is the same as the XAS spectrum for comparison. Then we analyze using the funnel line shape, which is caused by the interference between the continuum and discrete excitations. On one hand, for all the valence band emission, the parameter Q becomes infinity, and the spectrum is represented by the Lorentzian curves. On the other hand, Q becomes negative in the CIS spectrum for peak B. It should be noted that Q has been always positive in the previous resonant photoelectron spectroscopy studies so far as I know. The schematics of the excitation and decay process is shown here. Left, in the Titanium-3D peak, the continuum excitation is nearly prohibited because the photoexcitation cross-section of Titanium-3D orbital is very small, and the core level excitation and following the Auger decay is dominant. In the Selen4P peak, on the other hand, there is an interference between the continuum photoexcitation process, direct photoexcitation, and the photoexcitation followed by the interatomic Auger decay among Titanium-3 core and Selen4P valence band take place. Okay, we have shown here that the Selen4P derived band shows the final resonance with a negative Q at the Titanium-2 pH. The remaining mystery is why. I have no answer here. At this stage, the textbook says that the Q value in the final resonance is determined by the phase shift between two processes, discrete and continuum. In fact, negative Q is rather commonly observed in many fields, in many spectroscopies. An example is here. It is absorption spectrum of the helium atom in the VUV region. So we might better ask a question, a different another question that why Q is always positive in the conventional resonant photoelectron spectrum. The striking difference between the conventional cases and our case is that the observed electronic state is at the same atom of the core excitation atom or at a different atom. In this case, we observe the serine derivative peaks in the titanium photo core excitation. This should be related to the answer why, but more effort, particularly theoretical work, is required. This is the summary. Thank you very much.